everyone. So this week we're going to be moving on from trigonometry to now start focusing on some different types of graphs that are called conic sections. So there's going to be 4 different types of conic sections that we're going to be focusing on, and I have them kind of drawn out down here. So you might recognize at least a couple of them as types of graphs that you've learned how to graph in the past. So the first one here in red is what's called a parabola. So that one hopefully you have some familiarity with. Next picture here is a circle. So those are the 2 that you probably are already familiar with. So this next shape here is, it looks like an oval, right? And so the technical name for that is that it's called an ellipse. And then this last shape is what's called a hyperbola. So we're going to be focusing on these different graphs throughout this week. Starting with today, we'll be talking about ellipses. But before we get into that, I just wanted to give you some idea for why is it that these graphs are, what do they have in common, and why are they called conic sections? Because, you look at them and they all, at least most of them, look fairly different from each other. So what they have in common is basically if you take a cone, and when I say a cone, I don't mean just like an ice cream cone. I mean a cone that is has kind of 2 pieces to it. So I'm just drawing a rough sketch here because I'll show you a much better picture in a second. So if you have a cone, or it kind of looks like an hourglass where it's like one cone kind of connected to another cone. If you take that shape, so picture that's a 3-dimensional shape. If you take that shape and then you kind of intersect it with a plane. So what do I mean when I say a plane? Picture like a piece of paper. So picture that you have this 3-dimensional shape and you're kind of slicing into it with a piece of paper, and you're looking at what's the shape that you get in the places where those things intersect. And so what we'll see below in a second is that depending on how you position the plane compared to that cone, you're going to get one of these 4 shapes. So let me just bring this up. So here in red, we have the cone that I was talking about. And then this thing in kind of this bluish purple is the plane. And so what we can see is that if you take the plane and position it so that it's kind of like parallel with the sides of the cone and see what shape you get when you intersect, you get a parabola. If you position the plane so that it is horizontal, so like flat horizontal, then you're going to get a circle at the places where the plane crosses the cone. If you take the situation that gave you a circle and you just kind of tilt it slightly, then you'll get an ellipse. And then if you put the plane so that it's vertical and look at where it crosses the cone, you're going to get 2 intersections, and that gives you this shape called a hyperbola. So we're not really going to be like using this definition or this idea. It's more just kind of a nice piece of background information to know, just so you know, like, why are these things all called conic sections? Why are we talking about them together when they seem like they're so different? And that's really the reason why. So today, as I mentioned, we're going to be focusing on the ellipse and the circle. And really, the circle is a special example of the ellipse in the same way that a square is a rectangle, right? Like a square is a special type of rectangle. Similarly, a circle is a special type of ellipse. And so we'll really be kind of talking about both of them at the same time. So the main thing we'll be focusing on in this video is how to graph an ellipse and basically what its equation looks like. But before we do that, I just want to talk briefly about the geometric definition of an ellipse. And before we do that even, I'm going to talk about the geometric definition of a circle. So you might remember talking about this at the beginning of 141 when we talked about circles. We talked about how, if you imagine drawing a circle, how would you do it? Like what tools would you have to use to make sure it was a perfect circle? And one way you could do it is picture that you take a piece of string and you pin one end of it down to the paper, and that's going to be the center of the circle. And then you connect the other end of the string to a pen and kind of draw it around. That's going to give you a circle, right? Because what does that tell you about circles? Well, circles are the set of all points that are the same distance from the center point. So I'm going to write that down here. A circle is the set of all points that are the same distance, and that distance is what's called the radius, right? Like that's the distance from the circle to its center. And what's that specific point called? It's called the center of the circle. So what does this look like visually? Well, if you wanted to draw a circle, as I said, you could picture pinning a piece of string or something down and, using that to kind of sweep around and get a circle. And no matter where you go on the circle, this distance here is always going to be the same. So that's not true for an ellipse, right? For an ellipse, it is, just looking at the example on the previous page, it's longer in one direction than the other direction. So it's not that same definition, but we'll see that we can basically kind of just tweak this definition a little bit to come up with how we could think of an ellipse. So, and this definition I think is going to sound a little confusing until we draw it out. And I also have a video I'll show you, but just bear with me. So an ellipse is the set of all points such that the sum of the distances to two specific points. So now we're not talking about, we basically don't really have one center, we kind of have two centers. And what are these two specific points called? They're called the foci. And this isn't something we're really, going to be talking about. So you don't need to memorize that word or anything. But so foci, by the way, it's just the plural for the word focus. And we'll see a little bit later this week why it's called that. But yeah, so we're saying that any point on the ellipse, if you take the sum of the distance from that point to two different specific points called the foci, you always get the same number. So what does that look like? Well, basically, so let's say that here's our ellipse. So maybe the foci are here and here. So basically what we're saying here is that if you pick some random point on your ellipse and you measure the distance from that point to one of the foci, and then you also measure the distance from that point to another one of the foci, and you add them up. So here we're saying this green distance plus this red distance. If you then pick a completely different other point on the ellipse, like any point you want, so maybe I'll just pick here, and you measure again the distance from that point to one of the two foci, and then you measure the distance to the other one, all of these four distances are different, but what is the same is that the sum of them. So if you were to add up the length of this purple piece to the length of the blue piece, then you would get the same thing as you got by adding up the red and the green. So it's not that every point is the same distance from a point, it's that if you kind of compare that point with these two special points and add up the distances to those special points, you're going to get the same result regardless of what point you pick on the ellipse. So these 2 points here are what are called the foci. So how can we think of this in the same way that I talked about in the last example? I was talking about a thumbtack and a string and drawing a circle that way. Well, basically, if you now picture that this green and this red together are one string. So it's one continuous piece of string. And so you're pinning down two corners of the string, and you're taking a pen and kind of dragging it around in the oval. And so what's going to happen is that the proportions between the red and the green are going to change, right? We can see that because when we look at the blue and purple, they're different proportions to each other. But because it's one piece of string, it's still going to be the same total distance. And so that's what I'm going to show you in a video right now. So hopefully this isn't, I think it's a little bit pale because this person I think is maybe doing it in pencil. So hopefully you can see it, but I'll link this video in the description for this video. I'll link this other video in the description for my video. So basically you'll see that this person has two thumbtacks and one piece of string, and they're kind of going around and drawing all these different points. And so the ratio of those two distances changes, but the total distance stays the same. So what they're going to do next is they're going to take these two thumbtacks and move them, and we're going to see that that gives you a different ellipse. And so I just want to show you that, and I think this person goes and does it a few times, so I'll just show you like one more. And we'll see how the shape changes when you bring those 2 points closer together. So now they're one, notch closer in together. So notice that this ellipse ends up looking a little more like circular, right? It looks a little more round. And so basically, if you take these two foci and move them closer and closer together, the closer and closer together they are, the closer and closer the ellipse gets to being a circle. And if you get them so close that they're actually the same point, well, that's when it becomes a circle. Because if you only have one point, then you're just looking at the set of all points that are the same distance from that one point, and that's a circle. So again, we're not going to be like really using this definition or anything, but I just wanted to show it to you because I think it's kind of interesting. And I would encourage you, if you feel up to it, to try this at home with some thumbtacks and pen and some string. It's pretty easy. I've thought about doing it in class, but obviously we're not in class right now, so feel free to try it at home. Okay, so the next thing we're going to talk about, and this is kind of the most important part of this video really, is graphing ellipses and basically what their equation is. So I want to start by reminding you of what the equation of a circle looks like. And so in today's video, and for the beginning of this week, we're going to be focusing on graphing ellipses and other conic sections that have not been shifted. So we'll see later in the week what happens, how the equations change when they're shifted. But for now, we're going to be looking at things that are kind of centered around the origin. So I want to start by reminding you what the equation is for a circle. So recall that x squared plus y squared is equal to, and I'm actually just going to stick with x squared plus y squared is equal to 1 because we're going to use this to kind of compare to some of our ellipse equations. So what is x squared plus y squared is equal to 1? What does that look like? That's a circle, right, with a radius of 1 and a center of 0, 0. It's the unit circle actually, right? And that's the, so you might remember me talking about this back when we first started talking about the unit circle. You might think of the unit circle and think of all those angles. The unit circle is literally just a circle with radius 1 centered at the origin. So what we're about to draw is the unit circle. Is a circle of radius 1 centered at 0, 0. So I'm going to graph that because we're going to then kind of compare what happens to that when we tweak our equation a little bit. Not a great circle. I'll try to do it better. Okay. So my question for you is, what do you think happens? So what happens to the graph if we replace x with x over 2. So I'm going to make a new equation where instead of it saying x squared plus y squared is equal to 1, I'm just going to kind of tweak this equation and instead write it as x over 2. Actually, I'm going to color code this a little differently. Do it like this. X over 2 squared plus y squared is equal to 1. So I'd encourage you to pause the video for a second and think about this and like think about transformations. If you're doing a transformation where instead of x, you're doing x over 2, what is that going to do to the graph? So what it's going to do is it's going to stretch it by 2 horizontally, right? Because when you divide, think about graphing like trig functions. So when we did sine of x and then we did sine of x over 2 or 1/2 x, that actually made the graph wider. And so what this 2 is going to do is it is going to stretch the graph horizontally by 2. So what's that going to look like? Let me just rearrange this a little bit. So if we take our original picture of our unit circle and we just stretch it horizontally by 2, that means that the vertical part's going to stay the same. So it's still going to have the same kind of top and bottom, but now it's going to be stretched out horizontally so that has a width. It's almost like so I guess one thing to know about ellipses is that there's no such thing as the radius of an ellipse, right? Because for a circle, the radius is the distance from the center of the circle to the outside of the circle, and it's always the same. Whereas for an ellipse, that distance is not always the same. But you could kind of think of this as having like a vertical and a horizontal radius. And so the vertical radius is the same, and the horizontal radius became, I wouldn't, that's not the official term for it, but you can think of it that way. So the way that you would typically actually write this equation of this ellipse here is that you would square this fraction. So really the way that this would be written would be x squared over 4. Right, because you are taking this fraction and squaring it. But why did I start by writing it as x over 2 squared? Well, to help you kind of see where this shape is coming from, seeing the fact that the shape is coming from the fact that we're actually stretching horizontally by 2. So we can actually do the same thing for y. And this might throw you off a little bit because we're used to things kind of working differently horizontally and vertically. But basically, because the x and the y are on the same side of the equation when we're dealing with circles and ellipses, you can think of transformations as working the same for both of them. And so it will, like anything that you kind of do to change x and do to change y, they're going to affect the horizontal and vertical things the same way. It's not like one of them is opposite of what you think and one of them is the same as what you think. They're both going to be kind of opposite, if that makes sense. Hopefully that didn't sound really confusing, but you'll see in a second. So what about if we replace y with, let's try y over 3. So what would that make our equation? Now our equation is going to be x squared plus y over 3 squared is equal to 1. So like I said, because the x and y are on the same side of the equation, whereas when we're doing stuff like y is equal to sine of x, then x and y are on different sides of the equation, right? So vertical and horizontal transformations are fundamentally different because things are on different sides of the equation. Here, x's and y's are on the same side of the equation, so they're basically treated equally. And so if we take y and divide it by 3, that's going to give us a vertical stretch by 3. So if you wanted to write this equation more nicely, you would write it as x squared plus y squared over 9 is equal to 1. So what is this graph going to look like? Well, now if you think back to our original unit circle, you're going to leave the horizontal kind of dimension of this the same, but then the vertical dimension is going to get stretched to going up to a height of 3 and down to a height of -3. So it's going to look like this. So this is basically how it works. We'll see that all ellipses will have equations that kind of look like this one. And you're basically just going to be kind of seeing horizontally and vertically what its kind of measurements are and using that to sketch the graph. So I'll write that down as kind of a general fact, and then we will do a couple of examples. So in general, an ellipse has an equation of the form, and I need to move these around a little bit. Sorry about that. Oops. Okay, so as an equation of the form, x squared over a squared plus y squared over b squared is equal to 1. So notice I wrote a squared and b squared. Well, that comes from, if we look back to this example, that if you are kind of replacing y with y over 3, when you actually multiply that out, it's no longer 3, it's a 9, so it's 3 squared. And then same thing here, we replaced x with x over 2 to get that horizontal stretch by 2, but then in our final answer, we don't see a 2, we see a 4. And so the numbers that you'll see in the equation are going to be the square of what's actually happening in terms of that horizontal and vertical stretch. Okay, so an ellipse has an equation of the form this, and then we'll sketch the graphs in a second. So the graph will look like the unit circle. So it will look like a circle with radius 1 centered at 0, 0, but it will be stretched by A horizontally. So you can't take directly the number that's in the denominator, you have to take the square root of it. And we'll do examples like that in a second. And then stretched by B vertically. So what's that going to look like? Well, the general shape it's going to have is actually going to depend on whether A is bigger or B is bigger. So if the number in the denominator for x, so if that number A is bigger, well, then that means that you're going to have a graph that is kind of more wide than it is tall. I didn't do the best job with that. And why is that? Well, it's just because it's been stretched by more in the horizontal direction. So this distance here is going to be A, and this distance here is going to be B. And then, so this picture that I drew here is what happens if A is bigger than B, right? Because if A is bigger than B, then the graph has been stretched more horizontally than it has been vertically. If instead the stretch that's vertical is more than the stretch that is horizontal, then the shape of the graph is going to look more like this one. And so in this case, it's still, this would be A, and this would be B. So one thing I just want to quickly mention, I don't know how many of you are really following along in your book, but in the book, they kind of, they do something that I think makes this a little bit more confusing personally. They say ahead of time that A is bigger than B, and then they kind of write this equation two different ways. So they write it with having A be under X, and then they have another version where A is under Y. And personally, I just think that kind of adds more complication than there needs to be. But I just want you to be aware, if you look in the book, you might notice that things are a little different. But yeah, the main thing to just know is that whatever number appears under x squared, that's telling you about the horizontal stretch, and whatever number appears under y squared is telling you about the vertical stretch. And then whichever of those two numbers is bigger is going to tell you kind of like what direction is this ellipse bigger in. Okay, so let's do some examples of actually sketching graphs. So we're going to sketch the graph of never get things laid out right. We're going to sketch the graph of, let's do x squared over 9 plus y squared over 16 is equal to 1. So basically, we want to look at these two denominators and rewrite them as something squared in order to figure out what our graph is going to look like. So what is 9? Well, 9 is 3 squared. And I guess, am I being, now I'm not sure if I'm being consistent with my color. No, I just flipped my color, sorry. Let me switch that back. And then 16 can be written as 4 squared. So what does that tell us? That tells us that in the horizontal direction, our graph goes out by 3. And so we're going to have a point at 3 and -3. And then in the vertical direction, the graph is going to go out by 4. And so it's going to look like this. So you're basically taking the square root of what you see in the denominator in order to, oh my gosh, in order to figure out like how to actually sketch the graph. I am not doing well with this pen right now. Sorry, everyone. Okay. So just to make this really clear, so this distance ended up being a distance of 4, and this distance ended up being a distance of 3. Okay, let's do one more. So next one we're going to sketch. Actually, I lied. We're going to do 2 more. But one of them is a little different. So here we're going to sketch the graph of x squared over 25 plus y squared over 4 is equal to 1. So again, we want to rewrite each of these numbers as something squared to help us figure out what the actual stretch is. So 25 is the same as 5 squared, and then 4 is the same as 2 squared. And so that tells us that we should be horizontally going out a distance of 5 and vertically going up and down a distance of 2. And so that's going to give us a graph that looks like this. And so this 5 came from the denominator for x, and then the 2 came from the denominator for y. All right, I want to do one more example. I'm just going to copy this because I don't think I have another one. Okay, so last example I want to do is sketch the graph of x squared over 16 plus y squared also over 16 is equal to 1. So what's different about this one? Well, this one, we have the same denominator for both of them. So you could totally interpret this as an ellipse and just do it exactly like we did the last ones and say, okay, well, that means I have 4 squared here, and then I also have 4 squared here. And so that tells me that my ellipse is going to go out a distance of 4, and then also up and down a distance of 4. And it's going to look something like this. And so then when you look at this, well, it is an ellipse. It's a special type of ellipse. It's a circle, right? So how could you have known that this was a circle, without seeing that it was 4 in both directions? Well, if you took this equation and you multiplied both sides by 16, you would get x squared plus y squared is equal to 16. And if you remember how the equations of circles work, this number here is supposed to be the radius squared. And so basically we have a circle of radius 4. And so that's what I really mean when I say that ellipses, or that circles are examples of ellipses. It's because it's really just kind of a special case. It's the case where that A and B are the same that you actually get a circle instead of getting a more oval-shaped ellipse. All right, so that is it for today, and I will see you all next time.